Hello and welcome. This is the first in a series of lectures talking about Chapter 37, Wave Optics. Let's begin with a little storyline about this little bird. And for the record, this is straight from the textbook, so I'm just narrating. Time to take a break from studying physics and just chill out on your back patio. You're lying on your chaise lounge and enjoying the nice spring day. Suddenly, a hummingbird flies in, doesn't notice you, and lands just a few feet away. You hold still and watch quietly, amazed at the beautiful colors in the feathers of the bird, which seems to glisten. Then you notice, as the bird turns a bit, that the colors shift in their intensity and hue. You think, wait a minute, why would that happen? And then, in direct contradiction to your efforts to take a break from physics, you think, could there be some physics behind the appearance of the colors in the bird's feathers? The startled bird flies away in fear as you reach for your smartphone and fire up the internet. Let's begin. Hummingbirds look colorful, and if you were to look at one, you know, at an aviary indoors without a lot of sunlight or light in the room, you may notice that the feathers actually are not that colorful by themselves. The reason why they seem to glisten in the sun is that the sunlight, the colors of sunlight, interfere at different parts of the bird's body. So you get these bright, colorful spots throughout the feathers of the bird, because some colors, will bounce off with more intensity than the others, since the amount of interference does kind of depend on the color of light. So overall, there's a cool pattern that shows up due to reflection and interference of light on the bird's feathers. We've already seen how light can be warped by mirrors and lenses due to reflection and refraction, but those were just ray optics. So we should start talking about how the path of light can be modified by mirrors and lenses, but that did not have to take into account the wave nature of light. For this chapter and the next, we're going to talk about wave optics, which are physical effects that manifest themselves due to light's wave-like nature. So remember, mechanical waves, like waves on a string, can interfere with each other. They will overlap, even briefly, and depending on how they approach each other, they can create a bigger wave momentarily, or they can create a smaller wave. In fact, they can almost cancel each other out if they have the same amplitude. So this was the principle of superposition. And we saw destructive interference occur when waves approach each other perfectly out of phase, like in the GIF on top half. But if the waves approach each other in phase, then they create a much bigger wave, and you can see that on the bottom half of the GIF here, creating constructive interference. We saw the same thing happen with longitudinal waves, with two-dimensional waves like ripples in a pond. We even saw that happen with sound waves, which are another type of mechanical wave. So the question is, what is light? And is it a particle? Is it a wave? If it's a wave, then we should expect it to have this interference behavior that mechanical waves do. Now, back in the 18th century, people were still figuring out what light really was. You had Newton on one hand saying it was a particle, but then came Thomas Young, who was a young English physicist and a physician too, who in 1801 devised an experiment that could show that light effectively had the same behavior as waves when it came to interference. Now, what's actually happening? What's actually happening with light that we'll see causes interference of light waves is that light is actually a series of oscillating electromagnetic fields. So it's actually those fields that are overlapping that create what appears as wave interference to our eyes, as we'll see in Young's experiment. So, right, light is not actually quite the same thing physically as a mechanical wave, but due to its nature of being an oscillating electromagnetic field, its resulting electromagnetic field that happens from overlapping light beams creates an effect that is interference, just like mechanical waves do. So what did Young do? And again, like, people were still not sure what light really was. So he was the first person to show clearly that light could undergo constructive and destructive interference, just like sound waves, just like a regular wave. So he had to demonstrate this in the lab. So in a dark room, he took up a small barrier with two slits fairly close to each other, and the slits were really small. He shot a beam of light into both slits, and then on the other side, he put up a projection screen. Though that meant then that whatever light you shoot through the two slits should end up on the other side. And what he saw was projected across the viewing screen was a series of light and dark fringes. The idea was that if light was behaving as a particle, it would just shoot straight through the two slits and just kind of hit the area right in front of the slit. But this seemed to show that light was fanning out from both slits and creating these areas of constructive and destructive interference, just like ripples of water would do on a pond. So in the drawing here, you can kind of see how the two slits, once light enters both slits, they sort of become point sources for light, and you have these two ripples coming from either slit, and they reach the projection screen on the right side of the drawing, and depending on what phase they're in with respect to each other when they arrive at the screen, that's going to create brighter points or darker points depending on their phase difference. So to give you an idea of what's happening is that if you consider the space between the two slits on the projection screen, the light that reaches that point from either slit is traveling the same distance. Since light is being produced from the same lamp, from the same light source, that both slits get. In other words, the light coming out from both slits comes from the same source. So the light coming out from each slit is the same. They're in phase, they have the same wavelength. So that means that the path length for light from either slit is the same to this point O in the middle of the screen. So if both light beams travel the same distance, then that's going to be constructive interference. They're arriving in phase. And for constructive interference, the difference in path length, as long as the difference in the path length between light from slit 1 and light from slit 2 is some multiple of the wavelength of light, then constructive interference is going to happen. So throughout the slit, you have points like point B, where the phase difference is a multiple of the wavelength, so both waves arrive at a phase. Even though light from slit 2 is traveling a bit farther than light from S1, the extra distance it travels, it's equal to a wavelength or so. So when it arrives, it's still in phase with S1 and they overlap. You can actually see it in the drawing how when both light waves reach the point B, they're both just at a point in their cycle where they're just getting over a peak. Now there's other points throughout the screen, like shown in figure C, where the path difference is a half a wavelength. So you can kind of see how when S1 arrives at point R, it's just getting over a peak, but when S2 travels to point R, it's just getting over a trough. So they arrive exactly at a phase, so they overlap destructively and they flatten out. Their resulting wave is flat, so it's a dark fringe. Their light diminishes. Right, in the same way that constructive interference for sound waves makes a louder sound, and destructive interference makes a quieter sound. Constructive light waves are brighter, destructive ones are darker. Now, to do this experiment properly, like Young did, you need to make sure that the sources of light are coherent, so that the phase difference between each beam of light is constant over time. So that means that if they're rubbing out of phase at a particular point, then they're always going to be out of phase at that point or in phase at another point. And also, both sources, so both light sources from either slit should be of the same wavelength. If there's a variety of wavelengths coming out of each slit, then you won't be able to see an interference pattern, because at some points only some parts of the light will interfere and some won't. But when you have a single wavelength present, you will clearly see the points where that wavelength of light, those waves, overlap constructively or destructively. Now, this makes sense, right? Because when you think about it, in your house, you don't really notice destructive interference, between your kitchen light and your living room light, right? You don't see dark fringes in your living room when you have two lamps at the same time. The reason why you don't see destructive interference for your household lamps is because they're not coherent, so the sort of phase of the light coming out of your light bulbs changes super quickly, and also they shoot a bunch of light in like a big fan of different colors. So you don't get to notice any kind of interference, because the whatever interference is happening is always changing really quickly. So you need to have a very, very carefully designed experiment to make sure that the source is coherent. So just kind of an analogy to the double slit experiment, think about having two speakers producing sound waves, and at some point away from those speakers, the sound waves will overlap, and depending on the path length between R1 and R2, it's going to be louder or quieter. So this is the exact same thing that's happening with the double slit experiment. But instead of two speakers, you have two slits. And also, right, to actually notice a quieter or louder sound, you had to have the two speakers producing the same sound waves. So they were connected to the same amplifier, and they were emitting waves with the same frequency and the same initial phase. If they're just playing regular music, there's a bunch of frequencies there, the phase can change. So you won't necessarily hear sound interference at a house party. But if you're specifically creating waves with a particular phase and frequency, then interference will be notable. So the idea of the double slit, again, it's like analogous to the two-speaker setup for sound waves. So to ensure that you have a coherent light source to do this experiment, you should send the same light beams into both slits. That way, you know that they'll have the same wavelength and they'll be emitted in phase from both slits, and therefore it'll be coherent, and therefore you can see a pattern on the screen. Now, since you are the lab technician, right, you're setting this up, you get to control the light source. Now, nowadays, you might be able to actually know what wavelength of light is coming out of your light source, but Young did not know that. He could create a coherent light source, but wasn't actually able to, there wasn't any label telling him what the wavelength was. So why does diffraction happen? So what's actually called diffraction is it's the effect when light begins to diverge in all directions after moving in a single direction. So that's what's happening when light enters the slits. It diffracts. Light is first a plane wave before it enters the slits, and when it enters the slits, it spreads out in all directions like a ripple. So that happens according to Huygens' principle, right? It predicts that light emits these wavelets in all directions. So by that principle, as soon as it passes a slit, it's going to go in all possible directions. If that wasn't the case, if light did not actually diffract, which is what happens, but instead if light had like a particle behavior where it would just go straight through the slit. So whatever light could fit in the slit would keep going straight through. Everything else would just get blocked out, like in figure A. Then you only see two spots of light on the screen, and there will be absolutely no interference. You will not see the pattern that Young saw, but that's not the case. So how do we mathematically calculate where on the screen you'll see the interference, the bright fringes and the dark fringes? So to figure that out, right, we just need to think about the path difference. So let's just consider some point on the screen, and by some geometry arguments, you can figure out that the path difference, right, is just the difference between how much light from one slit travels versus how much light from the other slit travels. And there's an angle theta, which is the angle between point Q and point P. Point Q is right in the middle of the two slits. So the farther a point is from the center of the screen, the bigger theta is. Now, some quick measurements. D is the distance between the two slits, is a slit separation. L is the distance between the slits on the screen. And Y is the vertical distance, or, well, it can be horizontal. It will actually be horizontal, right? This lab setup you see would actually be on a table, right, spanning left to right. But because the drawing here, right, for clarity is shown on a vertical, the screen's like on a vertical axis. We call the distance from the center of the screen to the point of interest, we call that Y. But again, that's just like the position from the center of the screen to where the point of interest is. So to determine whether constructive or destructive interference happens at this point, P, we need to look at the path difference between R1 and R2. Let's call this path difference delta. And by definition, again, it's just R2 minus R1. Now, this is an approximation, but it is true provided that the path difference, or at the slit, as long as the slit separation is small and the viewing screen is much longer than that, which it was the case in Young's experiment and also a lab you did today, then the two beams of light approaching any point on the screen are more or less parallel. So you can draw a right angle triangle between the beams, as you see on the figure at the bottom. And that's actually a similar triangle with the triangle between Q, P, and O. So, that lets you write the path difference in terms of the slit separation times the sine of the angle between P and O. In other words, the path difference can be measured if you know the slit separation and you know how big the angle is between the center and wherever the point on the screen you're looking at. And that makes sense, right? Because the farther away the point is, the bigger the angle. So the path difference will be bigger. So there's two cases, right? Throughout the screen, there's interference, right? There's overlapping as the light beams overlap in different phases. But the bigger, more key points in the screen are where there's constructive and destructive interference, when they're fully arriving in phase or completely out of phase. Now, say they arrive in phase. That means that the path difference is a multiple of their wavelength. So this path difference, which can be measured using d sine theta, must be equal to some multiple of lambda. And then you have a formula that can tell you the angle to any bright fringe if you know the slit separation and the wavelength of light. And also, right, because there's multiple bright fringes throughout the whole screen, you have to specify the order number. So when m is 0, that tells you that the angular that the path difference between R2 and R1 is 0. That's a 0th order maximum. That's right at point O, the center of the screen. As m increases, either positive or negative, then you're looking at maxima, bright fringes, farther and farther away from the screen. For dark fringes, though, that's when the path length is a multiple of a half wavelength. So the formula for the angular position of the dark fringes is kind of like the one for light fringes, but now there's a m plus 1/2. So the first dark fringe can be found at m is equal to 0. Then the first order dark fringes are at m equal plus or minus 1. So the plus 1 will be above the center. The minus 1 will be below the center. And then the second order fringes, dark fringes, will be plus 2 or minus 2. So it's a lot like the light fringes, but now there's the plus 1/2 to indicate that the path length is that essentially the distance that R2 travels is some multiple of a half a wavelength, which means that it's going to arrive completely out of phase. So, right, the first maximum is right in the middle. Then the first order maximum are right besides it. So the 0th order maximum is one in the center, and you can find the position at that. If you set m to 0, that's going to give you an angle of 0, obviously, and then the maxima spread out from there, up and down. The minimum are in between the maxima, and m tells you what order they are. And realistically, the spacing between these fringes follows like a kind of like a trigonometric scale. But when you're looking at points on the screen that are fairly close together, they're near the center, much smaller than the separation between the barrier and the screen, the spacing between the fringes is pretty much linear. So rather than having to talk about the angle through the fringe on the screen, why don't we just talk about the position of the fringe? Yeah, so we can do that. Assuming that the fringe is not too small, it's not too far away from the center of the screen, then the angle theta is small, and that gives you a nice quick calculation to find the position of the fringes. So the right fringes can be found in the formula above, assuming a theta is small enough, which we can just default to assuming that. And right, you just have to know how your experiment's set up. So what the wavelength of light is, what the length of the separation is between the screen and the barrier. So that's L, the slit separation. And you also have to specify which fringe you're looking at. So again, M0 gives you the central right fringe, M1 gives you the neighboring ones, and so on. You can also find the linear position of dark fringes using the formula below. And again, right, there's the M plus 1/2 to denote the fact that it's destructive interference. So in your lab, if you're like Thomas Young, you can, you set up this projection box yourself. So you get to, know what L is. You get to know what D is because you built the lab yourself. And then on the projection screen, you see the fringes, or you can actually see the pattern. So you can measure the position of the bright fringes and the dark fringes. So if you know all that, then you can actually use these formulas to calculate the wavelength of light. And for like a small angle approximation we've done, the wavelength of light then, it's just a function of the pattern that you see, the slit separation, and the distance between the barrier and the screen. So here's a picture of what you may see if you do a double slit experiment at the lab. This is what Thomas Young saw, and this is showing an effect that could only occur if light is behaving as a wave, because if light were particles, there's no particle interaction that will allow particles to overlap and cancel out like this to create alternating points of intensity. So this for being like really early, beginning of 1800s, this gave a lot of validity to the theory that light behaved as a wave. And it wouldn't be for like another almost like 100 years where people were starting to rethink that and say, okay, wait, there's also some particle effects going on. What about that? So Thomas Young really kind of pushed forwards with the light as a wave theory, which would then be complemented by the light as a particle theory and then combined by Einstein and Planck later on. But it was a big deal for the time. It's kind of like the really first big demonstration of light having a interference effect. And again, why did we have to do all this lab to see this pattern? Is because we had to have a coherent light source, a single wavelength coming out in phase from both slits. Regular light sources produce light of different wavelengths, different colors, and their phase is always unstable, always shaking. So you really had to have a very controlled setup to see interference for light. So, quick quiz coming up. How do we move the fringes apart on the two-slit experiment? So, if you recall the formula for the position of the fringes, the position increases the farther away the screen distance is. It also increases with wavelength of light. It does decrease with the slit spacing, so it's going to be C. D suggests immersing the thing in water, but if you immerse a whole apparatus in water, that's going to decrease the wavelength of light, and that's actually going to decrease Y, which means the fringes will move closer together. So it's not D, it's C. So this is an example right from the textbook pages. I think it speaks for itself, but I want to point out something about it that is in this part. Basically, in this case, they're shooting two wavelengths of light through the slit, and they find out that the interference pattern from each wavelength overlaps at particular fringes. So for the shorter wave, the fringe it has of order 51 overlaps with the fringe of the longer wave of order 43. Now you can actually then calculate where on the screen the overlap happens, and according to the short angle formula for y, it happens at a distance of 1.3 meters from the center of the screen. But this formula assumes that y is much less than L, and in this case, the screen's 1.5 meters. So if you get a vertical position for a fringe that's close to L, like here, you can't use the short angle formula for y. You will have to use the normal formula where y is related to L times tan theta. And the only difference between this formula is that it will be almost the same calculation you see here, but you will have to divide by cos theta. And cos theta, right, is the angle between the center of the slits and the point projected on the screen. Anyways, it's also worth pointing out, right, that like the intensity of light projected on the screen isn't a binary state. It's not just like light, dark, light, dark, light, dark. There is a gradient of light that switches from high intensity and fades down to low intensity darkness, back to light, and so on. It's kind of hard to notice the gradient because of camera resolution, because of divergence of light, but there is a smooth continuation of light intensity through the fringe pattern. So we can actually calculate the intensity of light throughout the screen as a function of theta. Again, the angle from the center of the screen to anywhere else in the screen. And for points on the screen, for fringes on the screen near the center, you can actually measure the intensity with the formula shown above. So it's kind of like a small angle approximation of the intensity. And basically this formula, since it's using a cos function, it's a periodic formula, so that every s as a function gets bigger and smaller, the intensity will reach a maximum and then a minimum, right? Because cos has points where it's maximum and points where it's zero. So that represents the fact that as you go from left to right across the screen, you're hitting these bright fringes and you're also hitting some dark fringes. So if you plot the formula for intensity along the screen as a function of d sine theta, you basically get to see the intensity of light throughout the screen. So the image here with the red bands is kind of showing you the pattern you may see on a experiment. And the graph on the bottom shows you, right, a graphical representation, mathematical representation of what the intensities are throughout the screen. So you see how, at the bright spots, intensity is the maximum. At the dark spots, it's zero. We'll talk about this more in chapter 38, but you can also do a single slit experiment or 3 slits and so on. If you add more slits, you create kind of like secondary maximums. And still, the more slits that you add, the maxima is still the same. So if you look through the screen and you keep adding more slits, you still get the same light fringes at the same location, but they do get narrower. Also, it's worth pointing out that even though for the small angle approximation, it's not a physical effect that's happening, so we don't worry about that for calculating intensity throughout the screen. But in reality, the central fringe is always the brightest, so it's a bit taller than the other bright fringes. It's most intense light right in the center. And also, it's worth pointing out that as you add more slits, you increase the number of secondary maximum between each bright fringe. And also, as you add more slits, the secondary maximum actually gets shorter and shorter. So in this one, they're asking you to draw what the pattern may look like when you have 6 slits. So you expect it to have the bright fringes, the sort of like the highest points in the intensity of the pattern for 6 slits would still occur at the same location as if you had 4, 3, 2, 10 slits. But they do get narrower. So for 6 slits, the peaks should be narrower than for 5 slits. And also, every time you add one more slit, there's one more secondary maximum that happens between the slits. So for N5, you have 3 secondary maxima between each peak. So now you're going to have 4 between each peak. And they're going to be smaller than the main peaks by a factor of 1/36. So here's what the drawing will look like. Again, the central fringe is the tallest by a little bit. And there's 4 maxima between each fringe. And the right fringes are just a bit narrower than for n equals 5, but still wider than n equals 10. And the height of the secondary fringes, so the tiny little bumps, between lambda and 0 or 2 lambda and lambda, is 1/n squared, the intensity of the bright fringes. So it will be 1/36, the intensity of the bright fringes. Anyways, that's all for now. We're going to talk about thin film interference next time. So I hope to see